Welcome to our project presentation, Image Quality Assessment for a Diagnostic Imaging Department. This work was developed as part of the course Processing of Medical Images for Diagnosis. Our team consists of Alexia Castillo, Mateo Flores, Fernando Torres, and David Hernandez. In this project, we focused on analyzing and enhancing the quality of ultrasound images using both real clinical equipment and custom software built in MATLAB.
In Mexico City alone, the number of diagnostic imaging studies has increased significantly, reaching hundreds of thousands annually. This growth highlights the importance of maintaining high-quality images to ensure accurate diagnosis. Poor image quality can lead to misdiagnosis, unnecessary repeat exams, and increased healthcare costs. Despite this, many medical centers lack standardized protocols to evaluate image quality objectively, relying instead on subjective visual assessments. The main problem we address is the absence of standardized and validated protocols for image quality assessment in diagnostic imaging. This leads to inconsistent image quality across different devices and operators. Poor quality images can result in diagnostic errors, delayed treatments, and increased exposure to radiation for patients. Additionally, the lack of objective tools means that quality control is often insufficient, which affects patient safety and resource management.
Our general objective was to design and develop a set of tools to assess and improve ultrasound image quality. These tools were designed specifically for the context of the CI3M Imaging Center, aiming to make imaging evaluation more systematic and reliable.
In this project, our main objective was to design and implement a standardized protocol to objectively assess image quality in ultrasound studies. We focused especially on key parameters such as resolution, contrast, penetration depth, and uniformity, ensuring that the evaluation process could be consistent and reproducible. To support this, we developed a MATLAB-based tool capable of analyzing DICOM ultrasound images, calculating essential quality metrics, and enhancing image visualization through preprocessing techniques. Additionally, the tool is prepared to perform segmentation using methods like Otsu's thresholding and K-means clustering, laying the foundation for future applications in training, quality control, or diagnostic support.
The project involved both clinical hardware and a physical phantom. The ultrasound system used was the Philips Epic 7C, equipped with the X51 transducer. This system uses Ensite imaging architecture and real-time dynamic beamforming to deliver high-resolution images. For simulation, we built a phantom made of gelatin and laxative to replicate soft tissue. Inside, we placed silicone hoses to simulate arteries with normal anatomy on one side and an aneurysm of approximately 3 centimeters on the other.
On the software side, we developed a complete processing pipeline using MATLAB. This included loading and displaying DICOM images, with an integrated preprocessing tools such as logarithmic and exponential transformations, median filtering, contrast, adaptive equalization, and more. We also implemented optional segmentation methods such as iterative thresholding and K-means square clustering. Finally, we included tools to measure contrast, noise ratios, spatial resolution, and distortion.
Now, for the image quality assessment protocol, first we'll have to load and validate the DICOM file we're going to be using. Then we'll manually select the frame and calibrate it. And then for the image preprocessing, we'll perform some exponential or logarithmic transformations as well as some filters. After that, we'll perform some segmentation techniques, such as iterative thresholding and Otsu's method. Then, we'll calculate the image quality metrics like axial and lateral resolution. Finally, we'll also compute some advanced metrics like signal-to-noise ratio and contrast-to-noise ratio.
Although the final goal of the protocol is to evaluate image quality in echocardiographic studies, we validated it using a physical phantom simulating a vein. This allows us to assess key parameters like contrast, which is essential for separating tissue boundaries, the uniformity to detect artifacts, and the penetration depth to evaluate how well the ultrasound beam reaches deeper regions. Also, the axial and lateral resolution were measured to ensure the system can distinguish small structures. That is a critical requirement in cardiac imaging. And we also included S-on-air and CNR to assess how clearly targets are seen against background noise, and the geometric distortion to ensure that scale and dimensions are preserved, which is crucial in both vascular and cardiac diagnostics.
Let's now go over the results of our implementation. We analyzed two ultrasound views, the longitudinal and the transverse view, for which we applied a customized enhancement pipeline followed by both a qualitative and quantitative evaluation. On the longitudinal image, we started by applying a logarithmic transformation, which brightened our original image and also boosted the contrast as we can see. Then, we enhanced the image with Clahe to improve local contrast while avoiding overamplification of noise and medial filtering to the noise while preserving the edges. We then obtained the quality results, which showed improved separation of structures, especially vessel walls and tissue boundaries, increased detail and texture, which helps with diagnosis and later segmentation, noise reduction in the background making the image cleaner, However, we did observe a slight drop in the penetration depth, which is expected due to contrast enhancement favoring superficial layers. On the quantitative side, SNR improved from 9.84 to 12.86 decibels, surpassing the accepted threshold of 10 decibels for the diagnostic quality. CNR increased from 0.5 to 1.5, still under the ideal reference of 2.5, but significantly improved. Again, the analysis was applied in the same region for both images. Geometry distortion decreased from 1.32 to 0.80 mm, indicating more spatial accuracy. To close this view, we applied a segmentation stage. Thanks to the contrast enhancement, the simulated blood vessel structure was well defined, which confirms the effectiveness of the previous processing steps. Now, the transversal view. Here we applied a different enhancement strategy, exponential transformation to highlight brighter regions, contrast adjustment to rebalance the histogram, and low-passing filtering to smooth high-frequency noise that might have been boosted by the exponential transform. Eventually, this led to clearer textures, especially in the central structures, and slight noise reduction. However, penetration again slightly decreased, which we'll need to address in future iterations. On the quantitative side, SNR improved from 5.56 to 6.25 decibels, which is still under the ideal range, and CNR rose significantly from 0.25 to 1.26, almost reaching the diagnosis threshold. And as before, segmentation was successful, particularly due to the clear edges and contrast gain. In the image below, we can see the tissue segmented from the blood vessel.
To conclude, our tool shows promising results. It significantly improves image contrast, making structures easier to visualize. Additionally, it provides robust segmentation, which is particularly valuable for quantitative analysis. However, while both SNR and CNR values show improvement, they still fall below the commonly accepted diagnostic thresholds, specifically SNR above 10 decibels and CNR above 2.5 decibels. We also observed issues with image uniformity and penetration, which could impact their diagnostic reliability in clinical use. So, although the tool has great potential, it still requires further processing and refinement to reach optimal image quality for medical applications.